Hi everyone, what's going on? So today we're going to be talking about parity violation. And again, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page where you can find exclusive content that you won't find here on YouTube, and early content also. I'm starting things a little bit different now with the screen right in front of you so that we can jump directly into the topic. So let's get into this. So we're talking about parity violation today. In the last video, we talked about unifying the SU2 and U1 groups. Now we're going to diverge a little bit and talk about what parity is, how it's violated, and then we're going to move on. We're going to use these ideas to sort of come up with the concept of leptons, or the mathematical concept of leptons and quarks, and isospin. Anyways, we are starting now with looking at these gamma matrices. Right, so these are the gamma matrices we're all familiar with. These 0, 1, 2, 3, and 5. 5 is interesting. We skip 4. The reason this is one we haven't really come across, but gamma 5 is defined in this way, in which we multiply all of the other gamma matrices with an I. Okay. Now I'm not going to go through the monotonous matrix multiplication here, but this is what we get for gamma 5. Essentially, this can also be thought of as a matrix that looks like this, right? So it's a matrix of matrices, and it's an identity matrix across these two smaller diagonals. Okay, so we want to recall that we also have this different basis we can play with. This is called the mass basis, and the way we attain the mass basis is by defining this n here. This n here is defined in this way. You might think this is a little bit arbitrary, but this matrix is unique in that it has the property of this. Right, so if we multiply this by 1/2 of this, okay, then we get 1, or the unit matrix, the unit 4x4 matrix. Therefore, therefore we can define this gamma matrix in this way, because we're just multiplying. This got erased. We're just multiplying gamma 1, or gamma I, by 1, right? Because n times n inverse just gives us 1. So if we take our mass basis, or if we take our gamma 5 and put it in the mass basis, we're really just multiplying it by 1. We're going to put mass up here to call it mass. And then here we are going to, we're replacing n 1/2 with, or n to the inverse of n with n 1/2, right here. So here's that n, here's that 1/2. Okay. Then we just do the matrix multiplication here, right? So this is n, here's that 1/2, here's our gamma 5. And when we go through this, we see that we get this. So these two multiplied together gives us this. And then these two multiplied together gives us this. This 1/2 is going to take all these guys and bring it down to a matrix of matrices. Again, I've sort of shorthanded this, but this is just 1 along the diagonals. This is a 4x4 matrix with 1 along the diagonals. And these two first ones being -1 and -1, and then the other two being +1. So this means that in one form, not in the mass basis, we have a gamma matrix that looks like this, and in the mass basis, our gamma matrix looks like this. Both of them are essentially the same in some sense, because one, we're just multiplying by 1, but we've used an interesting matrix to show us that we can indeed put it in this form. And that, again, that matrix was the n matrix. Okay, so now we're going to take these two gamma matrices and we're going to define two operators using these gamma matrices. So here are these gamma matrices, and the operators we're going to define are called projection operators, and these are going to play an important role in defining how our Lagrangian is sensitive to parity violations. So this is how they're going to be defined, and if you just do the math, and if you kind of just do the math, we see that we get these guys here, because 1 minus this, well, we're going to get 2's in some places, right? And so we divide by 2, and we get the matrix looks like this, and we get a matrix that looks like this for our PR. So this guy here is going to be the left projection operator. This is the right projection operator. Okay, so a few things to note about these projection operators is that if we multiply them by each other, that gives us this property. So the square of the projection operator is the same as the projection operator. Same thing for the right projection operator. Here's an interesting property that's going to be useful for us later. So the Clifford algebra between these two operators, gamma 5 and gamma mu, is 0. Okay, you can show that just through matrix multiplication again. However, what this means is this, right? So if we expand out the Clifford algebra, it's just a different that swapped order with the plus sign right there instead of a minus sign. And we can bring this to the side. We can subtract this from both sides of the equation to get this guy. And what this means is that if we multiply our projection operator by gamma itself, gamma mu, that means we're multiplying gamma mu by this. And because of this relationship, we can swap the sign, because we can distribute, right? If we distribute, and all we have to do is swap the sign, and when we swap that sign, we can swap the two gamma matrices, and so we get a relationship that looks like this. Okay, this is interesting because the gamma matrix, when placed in the context of the projection operator, is just on the other side of the corresponding projection operator. Okay, so that's interesting. Let's go on to the next page here. And what we're going to do here is now we're going to see how the projection operator is sensitive to parity violation. So this projection operator only works on the SU2 part of Lagrangian, and let's see how and why. So this is so this here is what we're going to calculate. Right, so here, if we remember that this was an SU2, this here wasn't the SU2 spin 1 matrix, or series of matrices, right? Because remember, W mu was equal to that. This was sort of shorthand. Okay, so this is a matrix, so we need to put a matrix. This was a matrix here, so we could put a matrix here, and we'll see. Okay, let's see what this does. So we can square it, as we've seen before now, because it has that property. And we can expand that square, put it on both sides of the of this matrix again. And when we do that, this is going to be something interesting to know. I'll come back to this note here, because this is why parity violation is only sensitive to one type of the projection operator. But let's continue really quick with this calculation. So PL acting on our doublet, our solution, is going to give us, again, this is going to project just the left-handed chiral spinners onto that solution, right? Because if you recall, if our solution looked like this, had left chiral spinors and right chiral spinors, and our PL looks like this, well, we're only going to get left chiral stuff out of that. So we're calling this the left chiral doublet, or the left chiral spinor. Okay. Now we do some playing around here, right? So initially this was right here. This was defined in this way, right? With a mu. And then, so that's right here. And now we say this guy here is equal to this here, which is what we said before in previous videos. Just the gamma 0 matrix times the conjugate. And now we see here that this here is a PL just with gamma 0 on this side. Okay. And then we get this. So what we've seen is this is bouncing around, this sort of bouncing, inching towards the this guy here. And when we do that, see PL, and as it inches towards, it switches to PR, and then as it inches towards again, it switches to PL. And then when we do that, then we see that this whole thing can just be, we need to put a bar there. Oh, actually not yet, right? Because this is all just, oh, actually, yes, we do need to put a bar there, right? Because our gamma 0 defined that bar. Okay. And, oh, I see what I did. But anyways, and the point here is that all of this gets converted into this right here. We've the L sigma, or the doublet is we now have the L form of that doublet, and because of the conjugate, we now have this bar. All right, so this right here, remember this gamma 0 and this guy here made it so that we actually have this, and then this, and then that should be better. And if we notice that when we take a bird's eye look at this, this is the same form as this right here, just with the PL. So the PL basically is showing us that we can put, this is basically showing us that the PL, or just left chiral projection operator, when it's placed in a term that looks like this, which is in the Lagrangian, doesn't really do anything. It doesn't do anything at all to the Lagrangian, so it helps the Lagrangian remain invariant. But what it does actually is it's going to be sensitive to one very specific type of transformation, and we're going to see what type of transformation that is. It's going to be called the parity transformation, and we'll see why. But really quick to note, this PL, when we do this, this is going to be very important. When we expand out this square, notice that if this was an R, then we would end up with something that looks like this, because PL bounces to PR, which bounces to PL, right, making this guy an L. Well, if we started with PR, it would bounce to PL, then it would bounce to PR, and this whole thing would be an R, and then it would not be, this would not be the same form as this, because these two guys would be different from one another. So this is a crucial thing to note, is that only PL or only PR is going to work in this scenario. And this is going to be something crucial in defining what left chiral and right chiral spin 2 or SU2 transformations are going to be, how they're going to be thought of. And so we now want to parity transform this term of the Lagrangian. Now, what we're going to do here is going to go on exclusive content. I really just want to get to the point here before I move on to the exclusive content. So if you like this kind of content, make sure to hit that like and subscribe button. At this point, you can go onto my Patreon page and check out the rest of sort of the monotonous details of how this is going to go. I just want to show you really quick that the point here is that left chiral fields are going to be written as SU2 doublets with this is something that looks like this. So the left chiral fields are going to be actual doublets, and the right chiral fields are of this SU2 group are actually going to be singlets, right? Because we've seen now that right chiral and left chiral spinors actually transform in slightly different ways. Once you choose one of them, then the other one transforms in a different way. And the picture here is going to look something like this. And this is what the punchline is going to be. I'm just going to read this really quick for you guys, and then we'll move on to the exclusive content. So another way of thinking about this is that even though we have right chiral and left chiral spinors, or fields, only one of them is going to be able to undergo parity transformations and remain symmetric, while the other one must get demoted. Parity transformations therefore favor different spinors over another. That's one of the ways I kind of like to think about this. But anyways, make sure to hit that like and subscribe button, and I will see you guys in the exclusive content portion of this video on my Patreon page, where again you can just upon a small donation you can see more details about how this works. So I'll see you guys there. Okay, so we are here in the exclusive land now, and what we're going to do is we are going to talk about parity transformations. So when we parity transform these guys, these are what these parity transformations are going to look like. Okay, the parity transformations are defined in this way. So when we incorporate these gamma zero matrices, we have them defined. This is how these parity transformations go. Okay, so we've put them in here. We see this PL, it now becomes a PR. And we see all of these guys here. Well, this is negative. This is negative gamma mu if you multiply these guys together. This here is just a bar, so a sigma bar. This guy here, this is going to be negative W mu, because remember, a parity transformation of a 4-vector just flips the spatial components, making everything negative of each other. Okay, these two negatives make a positive, and what we get here is a PR now. This is interesting, but right, because we initially start off with a PL, right? PL. Upon parity transforming all of these items, there should be a parity transformation of this guy here. But upon a parity transformation of all these items, the PL actually becomes sensitive to that change in the parity transformation. So this does not equal this, and this means that the PL operator, or the projection operator, still makes this guy symmetric or invariant, but the symmetry is then lost when parity transformation occurs. We also note that only one projection operator is required to keep this invariant, and by convention we will say that the PL is the one that we'll use for this. We can choose one of them, but once we choose one, the other one can't be chosen. That's the point. So a parity transformation, just to summarize, looks something like this, and a Lorentz transformation looks something like this. So these are two different types of transformations. One's just flipping the sign, or flipping the entries in that sort of Minkowski metric, if you will. And in the case of the spinners, right, this is what that looks like. Again, we're just flipping, we're interchanging entries in that object. In physical terms, this means that the components of the left chiral boosts, which means these guys can transform into each other. In mathematical terms, the left chiral fields are written as SU2 doublets, like this, because they interact with this guy and therefore transform into each other. They therefore transform under 2D representation of the SU2 transformation. Now, this is what that transformation looks like. Contrast this with the right chiral fields, which are written as singlets because they're a separate field and they interact with these W matrices, but cannot transform into each other. They transform by the 1D representation of SU2, right? And that 1D representation is just e to the 0, right? So this means that a transformed sigma in the right chiral form is going to look no different under that transformation. And like I've said, another way of thinking about this is that even though we have left chiral and right chiral fields, only one of them is able to undergo parity transformations and remain symmetric while the other must get demoted. So, what does this look like in this picture I've drawn before? And this means that parity transformations therefore favor different kinds of spinors over the other. Left chiral, right chiral. So when we going back videos and videos ago, we were looking at these Lorentz transformations, and we found out that they can be represented by in different ways. The 1/2-0 representation, the 0 1/2 representation. This was the left chiral. This was the right chiral representation. And then we see how they boost differently and how they rotate the same way. Okay, that's all sort of been established. That is something that we don't really need to cover that much more anymore. However, one of the things that I do want to mention is that now we have the picture of the parity transformations. So when these operators interact with the SU2 transformations, the PL operator works for the left chiral representation, whereas the R operator, this is a little bit weird way of looking at this, but the point here is that one of these is going to be left chiral, the other one's going to be right chiral. This one's going to undergo parity transformations. This one can undergo parity transformations. This here again are Lorentz transformation. And this guy here, parity transformation. But what we saw was that only the left chiral, or only the left projection operator, was able to do the job of being invariant. Again, if we go back here, the left chiral field right here was the only one that was able to do that job of keeping the Lagrangian invariant. So when we're adding to the picture here, this left chiral invariant, or these left chiral objects are the ones that remain invariant under these parity transformations, whereas parity transformations for these guys actually are a no-go. Okay, because when we choose this one, then the other one has to not. It just doesn't work, which is what we've seen. So I hope that made sense. In the next video, we're gonna start talking about leptons, and we're gonna start putting some physics to this, which is gonna be fun and interesting. So again, if you like this kind of content, make sure to hit that like and subscribe button on my YouTube page. Again, you're here on Patreon supporting this, and so thank you for that support, and I will see you guys in the next video.